Good day, good day, good day, everyone. Once again, your favorite uncle is back. And of course, this time we'll be looking at question 7. All right, so if you haven't subscribed, please just make sure that you're part of the family, right? And of course, you can always like and share at the end of the video. And please, I'm asking you that, you can get in touch with us, obviously, on our email address. Okay, and that the details thereof will be found in the description of this video. All right, so let's get into electrostatics, right? So they say state Coulomb's law, that's 7.1 in words, right? Okay, so we know that Coulomb's law simply states that the force of attraction or repulsion, or you can say the electrostatic force between 2 point charges, is directly proportional to the product of the charges and inversely proportional to the square of the distance apart. So essentially, you're just stating what the formula actually states. All right. Right. So they say to us, we've got point charge A with a charge of positive 1.2 times 10 exponent negative 16, placed away 5 centimeters away from another point charge, which is B, carrying a charge of 1.52. So essentially what we see there along a straight line in a vacuum as shown below. Right, now they say an electron is placed at P, that is 4 centimeters to the right of point charge A. Right, now let's have a look at the questions. They say calculate the net electrostatic force experienced by the electron. Now, I want you to note in this case, so of course you've got the 2 point charges, both A and B, and you also have the electron, which is, at that particular point. Now remember, the charge of an electron, that would be 1.6 exponent or times 10 negative 19 coulombs. Okay, and we're given the charges of the two to be 1.2 and 1.52. Okay, so I've got 1.2 and 1.52 times 10 negative 16. Okay, all right, now we want the or rather the net force in this case. And please remember, it did say this is 4 centimeters here as well as 1 centimeter there. Okay, so now let's look at, so this is our electron. So I'm going to take the force between point charge A and the electron. So that's going to be KQA and multiplied by E divided by R squared. Okay, so that's going to be 9 to the power 9 rather. Okay, let me just write that properly. Okay, so that's 9 times 10 to the power 9, or rather exponent 9, multiplied by 1.2 exponent negative 16, and this is multiplied by the point charge of an electron, or the unit charge of an electron. Okay, so that's minus 19 over there, and divided by, in this case, our distance between point charge A and the electron is 4 centimeters. So that's going to be, remember, centi you divide by 100. So you say 0.04, or you can say 4 times 10 to the exponent negative 2. But remember, you must square that distance, right? Okay, so let's find that value there. So that's 9 exponent 9, okay, multiplied by 1.2 exponent negative 16, okay, that's multiplied by 1.6 exponent or times 10 negative 19, okay, and whoa, get a very big answer there, which is divided by that is 4 exponent negative 2. Okay, so that's negative 2, but remember that's squared, right? All right, so I've got that very big answer there, which is okay, you can say 108. That's minus 24. Okay, that's newtons. Alternatively, what you can do is, okay, I'm not too sure if my answer is absolutely correct. Please, you'd have to check that for me. For some of you, you probably might get something like 1.08 1.08 times 10 minus 20. That would be 22. Yeah, so that would be 22. All right, so that's what you'd get between charge A and charge B. Charge A and the electron. Now, obviously, now we look at B and the electron again. So we're going to do the same thing, charge of B and the electron divided by R squared. So again, Coulomb's constant, we've got 1.52 this time, times 10 minus 16, and the unit charge of an electron, that's negative 19. Okay, I'm trying to squeeze this in here. Okay, and this is divided by, now note in this case the distance between that electron and charge B is 1 centimeter, right? Okay, so that would be 1 times 10 to the power, or rather exponent, negative 2, and this is squared. Okay, right. So we kind of do the same thing. So that's 9 exponent 9 multiplied 1.52 exponent negative 16. Okay, multiplied by 1.6 times 10 exponent negative 19, right? This is just at the top. Okay, and we divide that by 1 exponent negative 2, but remember we square that. Okay, so we get an answer of 2188.8 times 10 negative 24. Okay, newtons. Remember, in this case, you could also express that, so that would be 2.19. Okay, so we can round this off. This would be 2.19. Okay, times 10. In this case, remember, we would have divided, this by 100. Okay, so in this case, so that's 10 negative 20. Is it times 10 minus 19? Yeah, something like that. Okay, right. So in this case, in fact, yeah, I'll just leave the answer as is. Of course, you can always use your calculators and find the answer in the most relevant way. I just need to find a way to change that back into scientific mode, and I think it's in engineering mode. Right, and then we wanted the net force, right? Now, remember, when we want the net force in this case, something I should have done before, remember what's happening here. You've got force A, or rather charge A, pulling the electron in that direction, charge B pulling the electron in that direction. So, of course, in this case, you can choose a positive direction. I'm going to choose the direction of charge B as positive, right? So I'm going to say, well, it means that my net force will be the force that B exerts on A, on the electron, right? Plus, remember, the force that A exerts on the electron is in, obviously, the negative direction. So you can take that, 2188.8 times 10 negative 24, and you subtract from it 108. So that's 108 minus 24. Okay, and in this case, I'm just going to take that answer and subtract that 108 negative 24. Okay, and the answer that we get there, let me see if I cannot change it into yeah, I want the scientific mode. No, I'm in the wrong place here. Okay. Yeah, okay, again, I'm in the wrong place. All right, no, it really doesn't matter. So in this case, I get 2080.8 to the minus 24. This is newtons, right? I'm still trying to wrap up in my mind just to find an easier way, of course, to express this. I think you may find, so if I move that up, in this case, I would need to, okay, right. All right, so in this case, that would be divide. So I would need to move this. All right, so this would be 2.08, okay. So let's see, if I move it 3 decimal places, so that would be, would it be minus 21? Please just verify that for me and let me know if that's the answer that you get. I can't find my other calculator so that I'm able to, verify it. I hope you understand. Of course, the method counts more than just the final answer. Okay, right. And then on the next question, they say to us, calculate the net electric field at point P, right? Now, ladies and gents, it's not necessary for us to actually now go the whole 9 yards and have to find the field and all of that. So we know that E is equals to force divided by the charge, right? So that's E is equals to F over Q. We found the net force there. And in this case, that's 20. I'm going to take that original answer because I don't trust the other one. Okay, so that's times 10 to the exponent minus 24. This is divided by. Now remember, which charge do we divide by? Of course, it would be the charge that obviously is sitting at that point there. And that would be the charge of the electron, isn't it? Okay. By the way, we said we're calculating the net force. I did not actually express the direction there. Remember, force is a vector. So in this case, I was supposed to say, if we're taking the points of a compass, this would be west and that would be east. So it means that the net force would be in the easterly direction. Otherwise, you could have just said to the right. Okay. Right. So in this case, then we say, all right, so we're looking for the field, the charge of an electron, that would be 1.6 times 10 negative 19, okay, and I take that answer and I divide 1.6 exponent negative 19, okay, I'm not sure what I did there, okay, yes, 2080.8, okay, that's minus 24, and I divide that by 1.6 exponent minus 19, okay, and I get an answer of 0.013, okay, and this is newtons per coulomb. Now, please remember, when we use electric field, our assumption is that we use a positive test charge, isn't it? Okay, so in that case, because we had put an electron, that's why the answer came out as, to the east. But if we were to put a positive charge, the answer would be to the west. Okay, or you can say to the left, depending on what your choice of direction is. Right, so we take the net force, and we took in this case the charge of the that is placed at that particular point, and that will become obviously the one that we divide by. All right, now I hope that you understood that. Right, now they say to us the electron is released from point P and accelerates towards charge A. Right, so now once they release it, of course, what's going to happen in this case, all right, it should actually, all right, so it means they've moved B. Of Of course, our electron is going to move in that particular direction. Okay, they say as the electron moves closer to point A, to point charge A, will the acceleration increase, decrease, or remain constant? Explain the answer. Now, please remember, ladies and gents, that, when we release an electron, the closer it gets, the distance in this case gets shorter and shorter, right? So in this case, we know that force is actually inversely proportional to the square of the distance, isn't it? Right? What does that mean? It means the smaller that distance becomes, the greater that force becomes. Okay, so as a result, remember that F net is equal to m times a, right? So it means that if we increase the force, in this case, it means the acceleration also increases, right? So that's what they wanted to find out, right? They say, will the acceleration be increasing? So definitely it will be increasing. And to explain that, all we simply say is that the force, the net force between the electron and the charge A is inversely proportional to the distance. So force is inversely proportional to the square of the distance. So therefore, the smaller the distance, the greater the force. Okay, this is me being lazy to write. Okay, so when distance decreases, force increases. So therefore, according to Newton's second law, acceleration, in fact, let's rather put it this way, acceleration is directly proportional to the net force. So the greater that force becomes, the greater the acceleration becomes. Okay, right, I hope that made sense, ladies and gents. And essentially, when it comes to this question, that is really how the cookie crumbles. And I hope that you are able to follow and understand. And please don't forget to like and share at the end of watching this video. Give us some really good comments as well. And of course, I am expecting you to help me out with a proper calculation there. Give us values on the comment section. Okay, right, thank you so much, and I'll see you guys next time. Sharp sharp.